Okay, I just want to make kind of an advanced footnote to the condition of a reservoir having both gas and oil. This is far beyond what's expected to know in the course and exactly why and everything. But I make this is kind of a. Has anybody heard the term? You say something. Well, I think this, but then you have the if, ands, and buts. Okay. What it means is that there are many. This is generally the case. Brazil has a great football team, but they may not win the World Cup because of this, this, and this. Okay, there's all these exceptions to why they might not win every year. So the if, ands, and buts with respect to a system being a gas and reservoir both. The one could simply be this first, what we talk about, which is the simplest, easiest. This is what you find in all the textbooks. But what you actually find in reality in maybe 1 of 10 or 1 of 50 cases is that you have gas and oil in the reservoir either because of gravitational segregation of individual components. And that leads to a variation of the composition with depth. Put in a very simple way, methane is lighter than benzene, is lighter than C50. So the light components will tend to segregate to the top because of gravitational effects, and the heavier components will tend to gravitate to the bottom because they're heavier. Okay? And if the system reaches some kind of an equilibrium where gravity and chemical forces are all in equilibrium, then you can get this kind of variation with depth of composition that actually puts gas on the top, oil in the bottom, let's say for a different reason. So this is basically reason A, this is reason B, you might have both. And the third reason is that the reservoir system hasn't come to equilibrium. If you waited an infinite amount of time, it might turn into a gas reservoir. It might turn into an oil reservoir. But today, because diffusion hasn't played out its role, gravitational segregation hasn't played out, you haven't brought the system to a true equilibrium because it takes geologic time to do that. We're at a state of non-equilibrium. And the state of non-equilibrium may say there's gas and oil today, even though all the laws of physics at time infinite would say that it's going to be only an oil or only a gas. Okay? So this is what we call basically non-equilibrium. And there are examples around the world of there either being gas and oil because of non-equilibrium, where if you went on forever, left it alone, it would turn into just a gas or just an oil. You also have the opposite case where you have only what looks to be a gas, but if you waited long enough, it might split into a gas and an oil. Okay? But of course, we're not looking at millions of years ahead. We're looking at what's there today. So reasons that you might have this two phases is because of non-equilibrium. Okay? That's just a footnote. You don't need to really understand it. So I'm going to give you a list of why being a reservoir gas versus a reservoir oil might be important. and I say might. Um, so let's see. Let's just kind of. And these are most of the things you covered in the group. So viscosity of gas versus viscosity of oil. Okay, generally this is looking like that, and sometimes and very often it's looking like that. Okay, it might be, they might even be approximately equal. You have to realize that viscosity can range for gas from 0.01 centipoise to about 0.1 centipoise. That's pretty much the range of gas viscosities, where it still has a dew point, where it's just a gas. 0.1 centipoise is very high for a gas. Okay? Kristen is getting close to 0.1 in Norway. And oil can have a viscosity ranging from about 0.1 centipoise to 10 million centipoise, and still make oil, still flows. So it's many orders of magnitude. Okay. The viscosity, if you don't know, everybody knows centipoise. I think that's water viscosity out of the faucet over here is about 1. Gives you a relative. The air viscosity is probably around 0.01 centipoise here. Centipoise, if you're big into SI units, is millipascal, same as millipascal. It's identical. Oil, we can go from 0.1 to 10 to the 6 centipoise. The higher the viscosity, the higher the pressure drop. Right? Because pressure drop is kind of proportional with viscosity. In pipe, in Darcys Law, right? Pipe flow, Reynolds, turbulent, or okay, it's viscosity is the higher the viscosity, the higher the pressure drop. The higher the pressure drop, that's both in the reservoir, in pipe, whatever. The higher the pressure drop, the more cost in general. The more expensive it is to develop a reservoir. Why? Okay, so if that's increasing, if that increases, then the costs will, generally speaking, always increase. Okay? What are the major cost items related to viscosity? The number of wells. How many wells you need to drain the reservoir. If you've got 1 centipoise, you might need 50 wells. If you've got 0.02 centipoise, it's a gas, you might need 5 wells. Okay? To empty the reservoir in 25 years. So the number of wells is a very important. The size of the tube, of the pipe, the size of the pipe, the diameter of the pipe. There are different pipes. There's the production pipe and there's the flow line pipes, and so the size or diameter of pipes. Okay, that's a cost item. The Japanese and Germans are going to take your money. You give a bigger pipe, you got to pay more money. Okay? So viscosity, we talked, y'all several mentioned it. And the 0.1 centipoise is kind of the threshold reservoir gas, reservoir oil, but it's not definitive like bubble point, dew point. Okay, but it's kind of giving you the transition from gas to oil is around 0.1 centipoise, approximately. What else do we have? I have, okay, we can say density, could be the same thing. The density of gas is typically less than the density of oil, right? So the density of gas is going to range anywhere from, at standard conditions, 1 to probably at the very greatest 300 kilograms per cubic meter. And oil will kind of start around 300-ish and go up to close to 1,000 for heavy oils. Okay? So, the higher the density, in general, the more expensive to develop the field. You have to get the stuff from the bottom of the well to the top of the well. And the more dense it is, more likely that you're going to have artificial lift to help get it out of the reservoir and to the surface. Okay? So generally speaking, the higher the density, the higher the costs. Okay? Density can have a big role in how you develop the field. Okay? If you want to make use of gravity to help you recover more oil. So the recovery or the development plan, and that goes the same for viscosity, so I should probably put this together. In both cases here, the reservoir recovery and development plans will be affected by viscosities. But these are kind of the transition can be the reservoir oil and reservoir gas densities could be very similar, and one could be a gas and one could be the oil. So the recovery factors and the development plans would be very similar, if not the same, whether you call it a gas or you call it an oil. Okay. But if the reservoir gas density is 100 and the reservoir oil density is 800, then there's a big, almost order of magnitude contrast. So it could have a big effect on both recovery and development plans. Okay. When it goes from the reservoir to the surface, okay, when it goes from the reservoir to the surface, somebody yesterday or Tuesday talked about a reservoir oil will always shrink, right? You start with 1 cubic meter of reservoir oil. What you get as as surface oil at the surface, obviously, the sellable oil will be less than that 1 barrel or cubic meter. Typically, it'll be anywhere from 5% less to a factor of 3 less. Okay? So we've got gas expansion we talked about versus oil shrinkage. Okay? And the shrinkage can be anywhere from a factor of 0.95. You start at the reservoir with a cubic meter, you get 0.95 cubic meters at the surface, to as much as a reduction of 1/3 of the oil, maybe even 1/4, 30%. The gas expansion will typically be anywhere from 1 reservoir cubic meter of gas becomes maybe 50 cubic meters of sellable gas, standard conditions, to as much as maybe an extreme 500 expansion. If it's a very high pressure reservoir, then it might expand as much as 500. That would be extreme. Probably typically 300 would be about as large as you get. But okay. So that's different. On Tuesday, several people mentioned that a gas can actually deliver at the surface some oil, right? That you get condensation out of the gas, It'd be like if we took the air in this room into the refrigerator, then you'll get condensation. Okay, you'll get some of the water will condense out as a liquid. Okay, you do the same thing. A reservoir gas comes to the surface, it goes to a lower pressure or lower temperature, and you get some liquid out. That sells today for $30 a barrel, which is not, it's like kind of depressing to think about. 2 years ago, I was teaching the class. I could have said $120 per barrel, 4 times more. It's crazy. Okay, but those molecules sold as a liquid at the surface actually have more value than if they're sold just as part of the gas. So, but the thing is that for gases, the density of this surface oil, and in this course I'm going to use the term O with a hat, meaning that the oil is at surface conditions. Okay, just for clarity. Okay, because up here I wrote oil. These are, if I write rho G or rho O, it's at some pressure and temperature other than standard. But if I write rho O, that's a sellable oil. It's a tank oil or a stock tank oil. Okay, so a tank oil coming from reservoir gas, I'm going to write it like that, versus if it comes from an oil reservoir, the surface oil you get coming out of a reservoir that's full of oil, those two sellable oil densities can be quite different. Typically, this is going to be like that. And the market will pay different amount of money if it's a lighter oil or a heavier oil. Okay, so there's some variation in dollars per stock tank barrel. I realize that's stock tank barrel. That's stock tank means standard condition barrel. Barrel is what, 6.28 barrels in a cubic meter. Is that right? Yeah. We'll talk about units later. See, there's, I think it's 6.28 barrels in a cubic meter. Is that right? Yeah. Okay. Anyway, so there's some price difference. If it's too light, then there can be a price loss. Okay? So there's kind of this intermediate region. And if you're selling in the part of the world like the United States, this is an interesting, this big shale oil production boom that they've had the last 5 years. It's one of the reasons that we have $30 oil. Because there's all this extra oil there. The Chinese are not buying enough oil. So the problem is that the refineries in the United States, they typically refine heavier oil. Okay? But all this oil coming from the shale production and the tight oil and the tight sandstones, all this new oil production in the United States is very low density oil, good quality oil, in fact, very nice oil. But the refineries are used to importing oil from Venezuela and other places, heavier oil, so the refineries refine heavy oil. So they have a hard time refining all this new light oil in the United States. So just in the last weeks, the United States lifted a ban on export of oil. They haven't been exporting oil for 40 years. Okay? The United States will always import oil, net. Okay? But what they need is they need to import more heavier oil and sell the light oil to the places that have refining for light oil. Okay? So they just released the ban on selling oil from the United States. By the way, the first big discovery in Norway was Phillips Petroleum, Ekofisk field. They're from Oklahoma. I have to tell you the Oklahoma stories. Okay? The first barrel of oil exported, you know who it was sold by? I don't know how they did it. ConocoPhillips, okay? These yahoos in Bartlesville, Oklahoma, okay? I don't know if they talked to the politicians or they had the barrels ready to sell, but they were the first ones to sell export oil from the United States after a 40-year ban. Light oil, they're a big player in the Eagle Ford down there, a lot of light oil. They wanted to sell it somewhere else, export it. And so there's a price effect. So this is value here. on what kind of oil it is, whether it comes from a gas or comes from an oil, in a sense. Now, these are all indirect consequences if it's a gas or an oil. It doesn't really matter. It's just saying that if you have a reservoir gas, the viscosity is less. You have a reservoir oil, the viscosity is more, but it's not really saying that things will be radically different if you call it a gas or an oil. Okay? But there is one thing that is radically different, and that is that in some parts of the world, and I think it may be limited to the Middle East, in the Middle East, several of the large producers when they make an agreement with an oil company to develop their resources, they say that, okay, you can develop our oil resources and we'll have a certain agreement on how much tax you pay or how much money or whatever. But any oil at the surface that comes from what is originally gas in the reservoir, we own it 100%. Okay? So, production of surface oil from reservoir gas, the state owns. Okay. Production of surface oil from reservoir oil, we have kind of a production sharing. Okay. I think the UAE is probably the biggest of this type. Arab Emirates, maybe Kuwait. I'm not sure, but anyway, this arrangement is some places. Now, Saudi Arabia, there are no external companies. There's no private companies developing their resources in oil. It's Saudi Aramco develops all of the Saudi Arabian oil resources, but they've let companies come in the last 5 years to develop their gas resources. So there, it's the exact opposite. If you find a gas reservoir, you get all the production. Okay? But if what you discover is an oil reservoir, thank you, it's ours, and you discovered it. Okay? So what you call the reservoir, a gas or an oil, has a big consequence on who owns what. Okay? So this has a big effect on value to the state versus to the companies. So that's another very practical and important consequence of whether you call it a reservoir gas or but it's limited in the world where this is going on. Maybe North Africa, some places as well. In the USA, there's, I probably shouldn't bring this in here because it's not really, some states have an arbitrary definition of what they call gas and oil. Okay, it doesn't use the dew point, bubble point definition, which is more rigorous. In some states, Oklahoma being one of those, I think probably Texas also, maybe all of them, but they define reservoir gas and reservoir oil based on when the reservoir produced to the surface. If you take the ratio of produced gas at the surface to the produced oil at the surface, the volume ratio, okay? They use the volume of surface gas to the volume of surface oil, okay? Coming out of the reservoir. And if that is greater than some, and we call this the producing gas oil ratio. Gas oil ratio. That's the short gas oil ratio. The symbol in the SPE is capital R, P for producing. Okay? If that producing gas oil ratio is greater than some state determined value. In Oklahoma, I think it's 10,000 cubic feet per barrel. That's about 2,000 cubic meters per cubic meter. And I think Texas is, I don't know, they're different numbers, okay? So each state may have a different number here, okay? So if it's greater than that, they call it a reservoir gas. And if it's less than that, they call it a reservoir oil. What is the consequence? The consequence says that because not one company owns the whole reservoir. One company owns maybe 1 by 1 mile. Okay? The reservoir may look like this, and this may be a 1 mile by 1 mile square. And basically the consequence it has, it says that if we call it a reservoir gas, you get one well in that 1 by 1 mile section. One well to drain that section by default. But if over here, so that would be reservoir gas, if the producing GOR over here is, let's say that that's 10,000 standard cubic feet per stock tank barrel for some state. So let's say that this is 11,000, and let's say that the GOR here was 9,000. Okay? In this section, you can, without really asking, drill 4 wells by default.
So within the same field, they can have them.
Exactly. Exactly. That's obviously going to affect cost, but also it could affect value. Because if you can produce as much as you want from these 4 wells, you may start draining, stuff from the neighboring sections that only have 1 well, right? Okay. So it has both an effect on cost and value and who owns what. So these are some examples where the actual formal definition is that a reservoir gas or reservoir oil has very important economic consequences.
Is this the initial producing GOR?
That would be the initial producing, yeah, that would be the initial producing GOR. That's right. I have to tell you a story. This is a true story. In Texas, back in the late 80s, early 90s, what happened is that in Texas there were some fields that were producing gas, maybe 20,000 GOR. Okay? And then some smart PVT guy, girl, I don't know who we're going to blame, said that, well, if we put a refrigerator on this well, okay, if we process it at the surface at very low temperatures, like if we cool this room to about like it is outside, you start condensing out water, right? And so they put on these low temperature separator facilities on these wells that would normally produce 20,000 GOR, and it brought them under the 10,000 GOR limit, which allowed them to drill 3 more wells, okay, on the section. They did this in a way so that, this whole field was developed with 1 well per section, probably was enough to drain each section. But then they started putting these refrigeration units on, and then they allowed themselves to go in and basically they could drill 3 more wells. Well, the guy with the 1 well already knew that it was enough to drain. But now you could say, well, somebody else could come in and drill the other 3 wells. Start sucking gas from the first guy's well. So it was kind of cheating, basically. It was kind of cheating. But the legally, because they used the GOR definition, and they didn't say how you process the stuff at the surface. And it was the initial. Basically, the initial had to be. So they could bring this below 10,000, then they could add 3 more wells. It's kind of a crazy thing. Okay. Does anybody know, looking at this, why would a state regulate the number of wells to the gas oil ratio? Does anybody have a feeling about that?
Because when the gas oil ratio will be low, it means there will be more oil compared to gas. So it means that, and because oil is more denser than gas, so and it needs more wells per unit area to recover the oil. So
Well, you're saying you need more oil. You need more wells to develop an oil field than a gas field. I mentioned that earlier, last hour, right? And that's true in general. But why?
Drainage area.
Well, the drainage area is fixed, 1 mile by 1 mile. Why do we need 4 versus 1? I mean, there was a logical reason in the 50s or 30s or whatever, for the state to have a regulation that if you produced what looked like a gas, that you need fewer wells than if you produce what looks like an oil. There is a good reason for that. And you guys learned about it, the Norwegian group learned about it last year, because you learned about Darcys Law.
because if the drainage area is the same, but for this same area, you need more wells for the oil.
Okay, but all right, you've had your chance. Let's see if I'm looking for one specific reason. The rate of drainage of a given 1 by 1 mile section will depend on permeability. Okay? Has nothing to do with the GOR. Right? Permeability is a rock property. What else does Darcy say? Actually, it wasn't Darcy that said this. What else has an effect on the velocity of flow in rock? Viscosity. Viscosity. So if it looked like a gas, which was, they used the gas oil ratio as and everybody doesn't measure a bubble point, dew point on their samples. They don't collect samples. But the gas oil ratio, some engineer said, well, if it's a high enough gas oil ratio, it's a gas. So they said, okay, 10,000 cubic feet per barrel. It's a gas. That means it's a low viscosity. Low viscosity means it's going to flow faster for a given pressure drop. That's what Darcy says. And you also learned, I think, last year in this course on well testing, right? Did you all learn about well testing? A little bit? There's a diffusivity constant, remember? Darcy says delta P, so we got 2 things going on here. We've got velocity is equal to K mu delta pressure, and then some geometrical distance term here, okay? How far away? Did they teach you last year that Darcy did not define this equation? Darcy's equation was defined like this. Okay? It was just a constant because Darcy was working with water. Dirty water, sanitation, water. And basically just observed the relationship between rate and pressure drop. It was linear. That was Darcy's law. Muscat in the 30s and Botset, and I don't remember exactly who, decomposed the constant into a rock property and a fluid property. Okay? This is interesting stuff. So it's got rock property. So the viscosity is going to, for a given pressure drop, is going to get the fluids at a higher velocity to the well. And then you also learned about this diffusivity constant. I hope you learned about it, which is K. Do you remember what it is, the diffusivity constant? I want the students from last year, the Norwegian students. Diffusivity constant. It's in well testing. It's the fundamental, you remember dimensionless time? Real time. And the proportionality constant is what we call the diffusivity constant. It basically, if it's low, then it takes a long time for that wall. If I start producing here, it takes a lot longer for that wall to find out that I'm producing here, right? If it's big, then that wall knows immediately, after 5 seconds, I started producing here. But if it's a low diffusivity term, then the wall doesn't know for another year. That's the diffusivity term. It's how long over there takes to know I'm doing something. Okay? That's the didn't they teach you about this? Yeah. So it's this constant here. It's K over phi mu total compressibility, and then some constant to make it dimensionless, whatever constant squared, some kind of distance. These are two fluid properties here. The gas compressibility is typically much higher, and the viscosity is much lower than liquids. Okay? So this diffusivity constant will be affected, will be different, will be higher in general for gases than liquids. And therefore, the 1 mile section will be drained more efficiently by gas, more quickly by gas than by an oil. Okay, so these are the two reasons for, but in both cases it's mainly the viscosity. Compressibility also comes into play a little bit. And basically they're saying that viscosity and compressibility are strongly a function of gas-oil ratio, which is true. And therefore, spacing, well spacing. That's what we call this, how many wells per area. That's the well spacing. Is a function of, in a sense, it's really the viscosity, but through the gas-oil ratio. Okay. So I think what we can say is that there are in some cases, very specific consequences of defining it as reservoir gas or reservoir oil, but they're really more political. They're, in both cases, the Middle East and the United States, they're really regulatory bodies who are enforcing, or the government's enforcing this arbitrary definition of what happens if it's a reservoir gas or reservoir oil. Okay? So it's a bit arbitrary. Okay, political. Okay. Let's see here. If there was anything else I had. Any comments or questions about this?
This rule is still applicable
In the Middle East?
in Oklahoma?
Yeah.
But now the definition of oil and gas based on initial GOR is changed, I think.
I don't know what I don't know what the current rules are. I think they're different for Texas and Oklahoma, probably Kansas. I don't know what they are, but there's definitely a well spacing default for gas wells and oil wells.
So is there any SP recommended definition?
No.
There isn't GO.
No. No. And in reality, the well spacing should be a continuous function of the viscosity, if you will. Okay, and of course permeability is probably even a bigger factor now. Because the permeability is clearly, this is clearly having probably the biggest effect. But that's a rock property, and they just ignore that completely. So.
Because usually if we find reservoirs that have initial GOR greater than 3,000, 4,000, we consider them as gas condensates. So they are considered as gas.
Well, yeah, I mean you can use different numbers, but fundamentally you have to go with the saturation pressure to formally define something as an oil or a gas.
Because I'm guessing that it will be really difficult to do that for the gas cap fields.
I'm sorry?
Like the state definitions will be difficult to be applied when it comes to gas cap fields, right? Because then it depends whether you producing
Well,
gas cap or
actually, there like in the UAE, there are some very large oil fields with initial gas caps, and for a long time, the owners and developers of the oil part of the reservoir were producing only oil, surface oil from reservoir oil. So they had this revenue agreement. Now, late in development, you're starting to get the gas cap flowing into those same wells. With the gas comes with it, as the air here, it's got liquid in it. So now some of the oil being produced is oil from the gas cap. They're very interested in having that quantified. Actually, we're involved in that, estimating that quantification, because that will change over time. And as time goes on, more and more of the production will be oil coming from the gas cap. And they want to know how much money they're going to get for that. So.
but how do you differentiate it if it's a mixture? It comes as a
This is complicated. So. The student assistants are going to try to put together an exercise related to this discussion, and I'm going to suggest a problem where we look at some kind of a reservoir that, just to make it, I'm going to make a stratigraphic trap instead of a structural trap. So this is the side view of the reservoir. So it's containing hydrocarbons. At some point in time, we have some initial composition, and I'm going to assume that it's uniform everywhere. Okay? And then what I'm going to say is that because of tectonic stuff are going on, or the geologists in the class, we're going to get this reservoir broken into three pieces. Okay, so we're going to have this part like that, and then there's going to be a fault here, and then we're going to have this middle section like that, and then we're going to have another fault, and then we're going to have this like that. Okay? So the reservoir was filled and has some hydrocarbon mixture, Zi, So the overall ZI we're going to assume here is the same for all three structures. We can call it L, medium, and high, low, medium, and high, and structure A, B, and C, whatever you want to call it. And based on my definition of what is a gas and what is an oil reservoir, I'm going to say that this is a reservoir oil. This is a reservoir gas, and this is a reservoir gas plus reservoir oil. Okay? And there's going to be three temperatures for this high another temperature for this here, and the temperature in the lower. And likewise, there's going to be an initial reservoir pressure in the lower. Okay, so the problem is going to be around how could this be? Okay, how could this be? They all have the same composition. They're originally all together. They have the same composition, but now because of this faulting and so forth, the middle section's moving higher. Typically, the temperature would what? Go down. Pressure would go down, right? You may have to rethink this. Reservoir gas at the bottom, reservoir oil in the middle, and reservoir gas plus oil at the top. Okay. So to help try to figure out, and they'll make some exercise and put it on It's Learning, how this, it'll be something related to this. And basically, how can this be? Okay, what are the conditions required for this to be the case? They all have the same composition. So, okay.